Hey everyone, welcome to this explainer. Today, we are diving straight into the math behind conservative force fields. We're going to peel back the equations and look at something honestly pretty profound about our universe. Why certain forces perfectly preserve your energy, while others act like invisible thieves, literally stealing energy right out from under you. Let's get into it.
So, picture this. You're pushing a heavy object in a massive circle, bringing it right back to the exact spot where you started. Now, sometimes the energy you put in perfectly balances out. You get it all back. But other times, that energy just vanishes. It's totally gone. Why does that happen? What's the mathematical signature that separates a fair, energy-preserving system from one that basically robs you blind?
All right, here is our roadmap for today. We'll start with the physics of conservative forces, move on to Stokes' theorem and curl, and then see the math in action with two completely different vector fields.
Section 1. The physics of conservative forces. Before we even glance at an equation, we really need to ground ourselves in physical reality.
The crucial point to remember here is that a force is defined as conservative if the work required to move an object between 2 points depends strictly on the start and end points. The path you take literally doesn't matter. And the biggest consequence of this is that the net work done around any closed loop has to be exactly zero. Basically, moving in a full circle costs you absolutely zero net energy.
To put that into a real-world perspective, think about gravity. Gravity is absolutely a conservative force. If you carry a heavy box up a flight of stairs, you're putting energy into that system. But walk back down to where you started, and gravity pays you back perfectly. The net work is zero. Now compare that to friction, which is totally non-conservative. Drag that same box in a circle across a rough carpet. You are fighting friction the entire way. You lose energy dragging it out, and you lose even more energy dragging it back. The energy is stolen, both ways.
Moving on to Section 2, Stokes' theorem and curl. Let's look at how this physical pushing and pulling translates into the math we need to actually spot an energy thief.
Now, Stokes' theorem is essentially the ultimate translator. It brilliantly bridges the gap between the macroscopic world, us physically walking in a giant loop, and the microscopic world. It does this by looking at rotation, or the curl, at a single, infinitely small mathematical point.
Here we have the theorem itself. The line integral around a closed loop on the left equals the double surface integral of the curl on the right. I know, it sounds like a mouthful of calculus, but think about what it's actually doing. It directly links the outside boundary of a shape, the loop you're walking, straight to the area inside it.
Let's break this down a bit more. On the left side, we've got our macroscopic loop, right? The total work done moving along the edge. On the right side, we have the microscopic curl. This right half is telling us that the total work done around the edge is just the accumulation of all the tiny microscopic swirls happening inside that loop. It's kind of like looking at a river. The overall flow around an island is really just the sum of all the little microscopic eddies and vortices in the water itself.
Which brings us to the golden rule of this entire explainer. If the microscopic curl, that nabla symbol cross F, equals exactly zero everywhere, the force is conservative. The logic is bulletproof here. I mean, if every single microscopic swirl is zero, then when you add them all up, the total macroscopic work around any loop has to be identically zero too.
All right, Section 3, Math in Action, Field 1. Let's take this golden rule out of theory land and test it on a specific mathematical field.
Let's bring in our first subject, Field 1, with its x, y, and z components. We're going to calculate its curl right now to see if there's any hidden microscopic rotation.
First things first, we set up our determinant matrix. When we expand this out and think about those cross derivatives, ask yourself, how does the z component change as we move along the y-axis? Well, it doesn't. The derivative is just zero. What about the x component along the z-axis? Also zero. Every single cross derivative cleanly vanishes here because the components only change along their own specific axes. So our final curl? Exactly zero.
So what's the big takeaway here? Because the math shows absolutely zero swirl, Field 1 is a conservative force. There is zero rotational shear. The math is telling us this field derives perfectly from a scalar potential function. If you were in a real physical environment modeled by this, moving a particle in a closed loop would cost you exactly zero net energy. Everything is perfectly balanced.
Moving to Section 4, Math in Action, Field 2. Now we're going to analyze a second field that behaves in a totally different way. Let's consider field 2. At first glance, its components look incredibly symmetric. It seems really neat and orderly. But we can't trust our intuition on this one. We have to rely on calculating the curl to reveal what's actually going on physically. We set up the curl determinant again. Actually, setting it up this time is a bit easier. Because our field only has x and y terms, it doesn't depend on z at all. So the I and j components vanish cleanly. That means all of our attention, all the mathematical heavy lifting, focuses entirely on evaluating the cross derivatives of the k component.
And boom, here is where that illusion of symmetry completely shatters. Think about the mismatch here. When we take the partial derivative of the y component with respect to x, we get a positive value over the denominator squared. But take the partial derivative of the x component with respect to y, and it gives us a negative value over the denominator squared. They are really close, yeah, but they are absolutely not the same.
Remember, the k component of the curl requires us to subtract these two values. When we subtract that negative term from the positive term, they don't cancel out, they compound. We're left with this massive fraction. But honestly, the only detail that truly matters here is this. It does not equal 0.
Because that curl is non-zero, field 2 is definitely not a conservative force. That mismatch we just found creates a subtle mathematical shear in the vector field. It acts just like a microscopic vortex. So moving a particle through this field in a closed loop means the field is going to do net work on that particle. Just like dragging a box against friction, moving in a circle here means energy is permanently lost or gained. The field is either stealing from you or pushing you, but it's never going to leave you exactly as you started.
Which leaves us with this honestly incredible realization to ponder. How does a hidden vortex-like property, tucked away in the cross derivatives of a purely mathematical equation, dictate the absolute physical laws of energy transfer in our universe? An invisible, microscopic mathematical swirl literally decides whether your energy is conserved or stolen. It's a beautiful reminder that math isn't just describing the universe. In a lot of ways, it's operating the machinery right behind the scenes. Thanks for joining me on this explainer, and keep questioning the math behind the reality around you.